In today's video, we'll learn about the first law of thermodynamics and Molar specific heat. First, let's start by trying to understand the first law of thermodynamics. The first law of thermodynamics is an energy conservation law that relates changes in internal energy. So if we have a system that undergoes a change from an initial state to a final state, where Q is the energy transferred to the system by heat and work is done on the system, the change in the internal energy of the system can be calculated by taking the amount of energy transferred to the system plus the work that is done on the system. If we're given a positive Q, then we know energy is transferred into the system by heat, and our Q will be negative if energy is transferred out of the system. We see that a positive work is positive when work is done on the system, and a negative work when the system does work on its environment. So we see that positive work done on the system increases its internal energy, while negative work decreases the internal energy of the system. And so if we look at our figure on the right side, we see that it states the first law of thermodynamics as the change in internal energy with a minus sign between the heat and the work, which we see is different in how we expressed it on the left side. The reason is that work is defined in these treatments as the work done by the gas rather than the work done on the gas, which is how we expressed it. So if we compare our work by looking at the amount of work that is done on the system, we'll have Q plus W. Or if we look at the amount of work that is done by the gas, we'll have Q minus W. Either way, the change in internal energy can still be calculated. So now let's see how molar specific heat and internal energy are related. We're given an equation for internal energy of an monatomic ideal gas with the equation that our internal energy is equal to 3 over 2 multiplied by nRT, or that our change in internal energy can be expressed as being equal to 3 over 2 multiplied by nR times our change in temperature. If we are given a molar specific heat at constant volume of an monatomic ideal gas, we express this as C with a subscript V, which is equivalent to 3 over 2 multiplied by our ideal gas constant. And therefore we can substitute our molar specific heat into our change of internal energy equation, which will give us a new equation that states that our change in internal energy is equal to N multiplied by our specific heat times our change in temperature. So our molar specific heat depends on the gas and can vary under different conditions of temperature and pressure. And we see that gases with a larger molar specific heat require more energy to realize a given temperature change. And we see to our right we have a list of some common substances and their molar specific heat listed. In our example, it states that 1 mole of neon gas is heated from 300 degrees Kelvin to 420 degrees Kelvin at a constant pressure. And we're asked to calculate the amount of energy that is transferred to the gas. So we know in part A, we can summarize our information given that we know that we have 1 mole of gas at an initial temperature of 300 degrees Kelvin and a final temperature of 420 degrees Kelvin. And we're asked to solve for Q. Well, we're given the equation that Q is equal to mass multiplied by molar specific heat times our change in temperature. See that we're given a change in temperature, our molar specific heat is given to us, but our mass is unknown. But since our molar specific heat is given to us in joules per mole Kelvin, we can use our mole for our mass, since our moles will cancel out. So we have 1 mole multiplied by a molar specific heat of 20.79 joules per mole times degrees Kelvin, multiplied by a change in temperature of 420 degrees Kelvin minus 300 degrees Kelvin. So when we multiply this through, we see that our moles will cancel, and our Kelvin will end up canceling with our change in temperature, which will leave our answer in joules. So we see that our Q value, when calculated out, will give us a value of 2,494.8 joules. In part B, we're asked to determine the change in the internal energy of the gas. So in part B, we know that we can calculate the change in internal energy of the gas by the equation that 3/2 multiplied by NR change in temperature we can calculate for our change in internal energy. And we can use this equation since neon gas is a monatomic ideal gas. So plugging in the values we know we have 1 mole of gas multiplied by the gas constant of 8.31 times our change in temperature of 120 degrees Kelvin. We see that our change in internal energy for the gas will be equal to 1,495.8 joules. And in part C, we're asked to find the amount of work that is done on the gas. So we know from our first law of thermodynamics that our change in internal energy is equal to our energy put into the system through heat plus the work done on the gas. Since we're trying to solve for W, we can rearrange the equation where we see that our work will be equal to our change in internal energy minus Q. And since we've calculated Q and our change in internal energy in part A and in part B, we can plug in our values to solve for the work done on the gas. Since our change in internal energy had a value of 1,495.8 joules minus 2,494.8 joules will give us a value that is equivalent to negative 999 joules of work, which means our change in volume must have expanded, which would result in a negative value of work, which shouldn't be a surprise since our gas is heated from 300 degrees Kelvin to 420 degrees Kelvin. We would expect that our change in volume would be positive, meaning that our value of work would be negative.